Hi everybody, this is a video for M2.T3.L1. We are looking at Module 2, Topic 3, Lesson 1, which is on an introduction to rational functions. And we're going to be looking at a lot of what about rational functions. So we're going to do a lot of these lessons. So the two key vocabulary words we need to understand by the end of the lesson are rational function and a vertical asymptote. And our learning goals is we need to do some graphs of some basic rational functions. We are going to compare rational functions in multiple representations. And we're going to compare the basic rational functions to various basic polynomial functions. And we're going to analyze them. We're going to analyze the key characteristics of these rational functions. So I'm going to skip the review and the getting started, which I believe you can manage on your own. We're going to jump to activity 1 for this video. And we're going to be looking at a function that is a very simple rational function. We'll define what a rational function is soon. So throughout this course, you've studied many connections between polynomial functions and real numbers. It follows then that polynomial functions also have reciprocals. Is the reciprocal also a polynomial? Is it a function? How does 1 over f of x compare to the original function f of x? So 1 over f of x is the reciprocal of a function f of x. So for example, if f of x is equal to x cubed plus 9, what is 1 over x cubed plus 9? What does that look like? So it's like we're putting the function in the denominator. To begin answering these questions, consider the reciprocal of the basic linear function f of x is equal to x. So we're going to take a real simple function, the real basic linear function, and we are going to take the reciprocal of it to get 1 over x. Okay. So they have some tables of values here. And we have what is x, what is f of x equals x, which is the polynomial function. And you'll notice they're exactly the same because the polynomial function f of x is equal to x, basically you plug in a number, you get that number back out. And it's the same over here. These are just the positive x's. And you can see you just get this line. It has a y-intercept of 0. It has a slope of 1. If you plug in 5, you get 5. So you get the 0.55, for example. It's a line. It's a perfect diagonal line. So now we're going to do 1 over x. Okay. And so for negative 6, it's going to be 1 over negative 6 or negative 1/6. Okay. This will be negative 1/5, negative 1/4, negative 1/3, negative 1/2, negative 1 over 1, or just negative 1. 1 over 1, or just 1. 2 over 1, or 1 over 2. 3 over 2. Sorry, wait, 1 over 3. Sorry, it's 1 over the number. 1 over 4, 1 over 5, and 1 over 6. These are tiny fractions. We're going to do the best we can to graph them. Okay? It's not going to be easy. Okay. Negative 6 comma negative 1 over 6. So here's negative 6. Negative 1 over 6 means it's going to be like really close to the x-axis line, but it's going to be below it. Okay, so that was the point. Negative 6, negative 1/6. All right, now we're going to do negative 5, negative 1/5. Negative 1/5 is going to be a little bit further down. Negative 1/4 is going to be a little bit further down. Negative 1/3, a little bit further down. Negative 1/2, halfway. 1, 1. Okay, so, or -1. So you can see these numbers are actually getting bigger until they get to -1. And we get, I know it's hard to do it because they're such tiny numbers, but it's curving. I want you to think about what happens right here. What happens at a half? So they didn't have that in our t-table, but let's plug in a -1/2. What do you get when you do 1 over -1/2? Well, it's going to be negative. And then think of it this way. How many halves go into 1? The answer is 2. So it's -2. So that's actually an extra point that will help you see what's going on. When we plug in -1/2, you get 2. It's curving. It's curving quite dramatically, actually. All right, let's go ahead and do the positive version. So over 1, up 1. Over 2, up 1/2. Let's zoom in here. Over 3, up 1/3, then a 4th, then a 5th, then a 6th. It's curving. It's getting closer to the x-axis. And if I were to plug in a positive 1/2, I'd get 2. So we plotted the points. Now we're going to draw a smooth curve. Okay, so the curve from the points that we have are going to look like this, just for the ones that we have. We need some more points maybe to kind of see what's going to happen. And this would be a good point to identify what's happening on Desmos to kind of back up what we're looking at. So let's go ahead and take a look at Desmos. And we're going to type it in. Whoa, this is what it looks like. So when you're in Desmos and you want to see specific points, you can click on the little gear and click a table. And you can see -6, -5, -4, -3, -2, -1. Now we didn't plug in 0. 1, 2, 3, 4, 5, 6. So those are your fractions in decimal, but we also plugged in a half, and we saw that it was 2, and a -1/2. So those are the points that we had plotted. You can see them plotted on the graph now. What if I plug in a 1/10? That's this point right here. It'll give you 10. It's like it takes the reciprocal of it. Okay, what if I plug in -1/20? -1/20. Well, you take the reciprocal of that, you're going to get -20. That's down here. Okay. So, I mean, what we can see here is that as we go to the right, it's going to keep sitting on top of that x-axis. But if you zoom in, you can see that it's not actually touching the x-axis. It's getting smaller and smaller. And over here, what's happening here as we get closer and closer to 0. So I typed in like -1/20th, which is like really tiny over here. It went all the way down to 20. What if I type in, what if we try -1/100, 1,000? Oh my gosh. I did 1/100,000 gives me a -100,000. I'm not going to scroll down, but that's like way far down. Okay, it's getting really big in the negative sense. And if I was making it positive, it would make it really large positively, right? The 100,000 would be up. So what does happen when we plug in 0 though? Of according to Desmos, it's undefined. So let's think about this. Let's sketch our graph. So what I want you to do is I want you to sketch it going closer and closer and closer to the y-axis, but don't cross it. Draw an arrow. And then this part is going to get closer and closer and closer to the x-axis, just sitting right on top. And then it's going to keep going. And then this side over here on the right is going to go further, left is going to go further down. And this way, sitting underneath the x-axis. So this graph has a name. It's called a hyperbola. Not all rational functions you'll learn are hyperbolas, but this is a hyperbola. Now, there's another table right here, and we've already kind of completed some of these, so we're gonna do these. So -1 over -1. This one turned out to be -2. This is -10, -100. 0 is, I'm going to write the word underneath, undefined. And that is because you cannot divide by 0. 1 over 100 would be 100. 1 over 10 would be 10. And then 2, and then 1. So those were some of the points that I actually talked about when we were looking at Desmos, and we were looking at them up here as well. So that's what's gonna, if you plug in 100th, it's gonna go up to 100. But if you plug in a 10th, it's gonna be up to 10 right there, for example. Okay. So I want to focus on some of these questions, but not all of them. I want you to go ahead and do B on your own. But C says, describe the end behavior of g of x. So the end behavior is looking as you go to the right or to the left. What is the graph doing at its ends? Okay, so that we can probably format this the way that you've done end behavior before, which is asking what happens as x approaches positive infinity and what happens as x approaches negative infinity. So as x approaches positive infinity, what, in other words, goes to the right? What does y do? Let's look at the graph. So as x approaches positive infinity, is going this way. We're looking at this end right here. We can see that it's just basically getting closer and closer to 0. If we go back to Desmos, that was this part where, as I'm scrolling along, you see 0.015. It's 0.014. I could scroll over here for a long time, and it's never going to cross that x-axis. And it looks like it's on the x-axis, but if you zoom in, you will see it's not. It's just sitting on top of it, and you can see the y value is 0.0026. How far can I go out? Okay. 9.8 times 10 to the 7th. We're in the millions. Or, yeah, multi-millions now. Okay. Whew. Okay, now I'm going to zoom in to see that line. So one thing you should know about Desmos is it has limitations. When I go right here, it says the x is 9.499 times 10 to the 7th and the y is 0. It's not really that the y is 0. It's just I went so far out, the math is way too complicated to actually for it to handle. In fact, it's not even letting me zoom in anymore. I just kind of broke it. But I want you to think about what 0 means and how are we supposed to get 0. If you're supposed to be dividing this 9.8 times 10 to the 7th into 1, okay, 9.8 times 10 to the 7th is, or whatever it was, it's 8 and then 6 zeros. It's 98 million. If you take a dollar bill and divide it into 98 million pieces, those pieces are going to be remarkably small, but they are not going to be nothing. They're going to be insanely small, but they are not 0. Okay, what Desmos is telling us by saying it's 0 is, I'm rounding to 0 because I can't handle the calculations. It's too hard. And so this is called grapher error. It can't go, I cannot zoom in anymore. It can't handle this. And so it's rounding to 0, but technically you need to understand it's not 0. Okay, it will never get to 0. So back to that question, which was C. Or I thought I was writing on C. I guess I wrote on B. Hold on, let me move that back down. Okay, we're doing C together. As x approaches positive infinity, y approaches 0. And if we go to the left, as x approaches negative infinity, it's just doing the same thing, but it's doing it from the bottom of, it's going from the negative side, but it is still approaching 0. Okay, explain your reasoning in terms of the graph equation table of values. We can see on the graph, right? We can see that it is doing this from the graph. From the equation, we know that if you plug in larger and larger numbers, like 1,000,000, this becomes smaller and smaller. If you plug another 0 in, it's just going to get smaller. Okay. Let's describe g of x as x approaches 0 from the left. Explain the output behavior of the function in terms of the equation. Okay. As x approaches 0 from the left, all right, so what are they talking about? They're talking about this. Okay, as x is getting closer and closer to 0 from the left, the graph, I think I accidentally deleted some important parts there, so let me just put that back. Okay, that the graph is going down drastically as it gets closer to 0, right? Because we're getting smaller and smaller numbers. When you take the reciprocal of a really tiny number, it becomes really large. Okay. We can say that g of x, the function, is decreasing rapidly. And you can describe as your explanation something along the lines of, when you divide negative numbers, tinier and tinier negative numbers, they become larger and larger negative numbers. Right, negative 1,000,000. And then as we go from the, as g of x, what happens to g of x as x approaches 0 from the right? So from the other side, it's rapidly getting more and more it's increasing dramatically. So say it's increasing rapidly, and that's because you're plugging in tinier and tinier things. You could write it as a fraction, like a millionth would be 1 over a millionth is a million. How many millions go into million, or go into one? A million. Okay. Okay, I'm going to jump to number 3. This is a key characteristic of this graph. Does the graph intersect the horizontal line y equals 0? This is also known as the x-axis. In other words, will y ever equal 0? Is there something I can plug in to x that would make this 0? Well, it's not 0 because 1 divided by 0 is undefined. And if we plug in a large positive number, you get something incredibly small. Okay, so that is a small number, but it is not equal to 0 exactly. If you plug in a negative number, it's incredibly small, just negative, but it's never going to equal 0. So the answer to this question simply is no. It is impossible for 1 over x to equal to 0 for any x. You can plug in a million things. You're never going to get it. Okay, does the graph intersect the vertical line x equals 0? In other words, can I plug in 0? No. 1 over 0 is undefined. Okay, and what that's giving us is this unique shape where y equals 0 is this orange dotted line that I'm drawing. It does not touch that. And x equals 0, which is also known as the y-axis, is this dotted line right here. The graph does not touch that. Okay? These lines are actually have a name. They're called asymptotes, and you're going to do a lot with asymptotes in this topic. This yellow one that I drew is called a vertical asymptote. And the way you spell asymptote is A-S-Y-M-P-T-O-T-E. And this one is a horizontal asymptote. And this one basically shows a specific type of end behavior. Vertical asymptotes come from specifically things that are undefined. As we saw in this case, x cannot be 0 because it makes the function undefined. It creates the vertical asymptote. And I'm going to jump to the number 4 now, where we're going to look at how do we describe the domain and the range of these. And actually that's part C on this. Describe the domain and the range of this one. And then we're going to look at different notations we could use to describe the domain and the range. So basically the domain is, if we look at the graph, everything but 0. The graph is, you can plug in any number you want for x except for 0. Okay, and the graph doesn't go there. And that's what creates this vertical asymptote. So for C, the domain, how do you describe all real everything but 0? You can literally say all real numbers except for 0. I used the wrong except there. Whoops. And then the range is your output, your set of all your outputs. And in this case, we can get every single possible number, but we cannot get 0. So it's the same, all real numbers except for 0. So you could write it in words. I just wrote it in words to describe it. Here's an example for what if your domain in your range is all real numbers except for 4. Other ways that we can write our domain in the range is with inequalities, interval notation, and set notation. So if we're doing inequalities for the domain, we would say, well, x can be greater than 4 or x can be less than 4, but that excludes x equaling 4 because we don't have an equal to on either of these. Everything greater than 4, everything less than 4 will work. That in the interval notation is shown below. That's where we use the parentheses and the infinities. This is basically saying from negative infinity to 4 and from 4 to infinity with a union symbol in between. And with set notation, the way that you read this set notation is this set notation uses these little curly braces. And we read it all x such that x is not equal to 4. And then for the range is using the output or the y's, or we would use g of x because that's the name of our function. If our range is the same, it's all real numbers except for 4, we would say g of x is greater than 4 or g of x is less than 4. The interval notation looks identical because there's no x or g of x involved. And then the range, we're just replacing x with g of x. All g of x is such that g of x does not equal 4. Okay, so go ahead and try writing our domain and range, all real numbers except for 0, which is the same for both domain and range, using each of these notations. Okay, go ahead and pause it and give it a try. And then when you're ready, I'll show you the answer. Okay, go ahead and check your answers. Pause it if you need to read through the answers. But pretty much this one was just replace the 4 with the 0. So then next, they finally give you a definition of what is a rational function. So the one that we were just working with, 1 over x, is the very simple example of a rational function. But the definition of a rational function, make sure to put this in your notes. A rational function is any function that you can write as the ratio of 2 polynomials. So you can write it in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. So if you can imagine a polynomial divided by a polynomial, you have a rational function. Okay, now in the case, a polynomial could just be a number. Like in our case, 1 is a polynomial. Or it could just be a variable like x, or it can be much more complicated things like your numerator, say, is x squared plus 3x plus 2. And your denominator is a line, 5x minus 7. That's going to give you a function. That's technically a rational function. Okay. Now, there's all sorts of patterns that go on with rational functions, as we'll see as you dive deeper into this. Okay. Recall from your study of exponential functions that a horizontal asymptote, okay, a horizontal asymptote is a horizontal line that a function gets closer and closer to. In most cases, a graph never intersects a horizontal asymptote, but in some cases it does. And you will see some of those cases as you study rational functions. Okay. In this problem, the function g of x has a horizontal asymptote at y is equal to 0, and it didn't cross it, right? Given the horizontal asymptote, you can express the range of the function, right? So we talked about how to write the range in all these different ways. The horizontal asymptote in this case affected the range. That's what they're saying. But we also had a vertical asymptote. So the function g of x equals 1 over x has a vertical asymptote at x equals 0. A vertical asymptote is a vertical line that a function gets closer and closer to, but never intersects. In this case, there's not a maybe it will intersect. It does not intersect a vertical asymptote, okay? So why? And it says right here in the little take note, a graph cannot cross its vertical asymptote because the function is undefined at that value. Okay, usually, or I'm not usually, all the time, an asymptote occurs for input values that result in a denominator of 0. So dividing by 0 gives you a vertical asymptote. The horizontal asymptotes are more complicated in how they come about, but the vertical asymptotes are very clear. If you can divide by 0, you will get a vertical asymptote at that x value that gives you 0. And sometimes that's 0, sometimes it's something else. Okay, now how do we draw asymptotes? Well, I showed you kind of a dashed line. So you will often see vertical asymptotes represented in textbooks and graphing technology as a dashed or solid line. Usually like a different color, maybe it's just dashed, it depends. The convention used in this textbook is to represent it with a dashed line. Now, I showed you Desmos. When you looked in Desmos, let's go back home, they don't do anything. They don't draw the asymptotes for you. You can draw them. Absolutely, you can draw them. We know what they are now. It's x equals 0, 0, I typed 9, and y equals 0. What I like to do if I'm making this in Desmos is I like to make them dashed. You can do that if you want to. And I might make them the same color and dashed. And I'm going to make it so that I can see things a little bit thicker. So you can see it's now, there's the asymptotes. But it's not necessary. If I make these go away, you can still see kind of where they are. We can visually see them. It's just we don't have them drawn. All right, let's, I think, leave it at that for this. You should try out 1 over x squared in activity 2 to kind of see how that one works, as it's a little bit different. So it's an interesting one that you get when you do 1 over x squared. And then you're going to model a situation, a real life situation using a rational function. All right, so there's your introduction to rational functions. Enjoy.